B. Remember what Ka is? Ka is the equilibrium constant, which corresponds to the reaction of a Bronsted base with water and nothing else to make hydronium ion and the conjugate base of the acid. Kb, base reacts with water, the solvent, nothing else, establishing an equilibrium between the conjugate acid of that base and hydroxide ion. Because in order for any species to be able to function as a Bronsted acid in water, it has to be capable from a measurable extent of reacting with water to make hydronium ion. Base has to be capable of reacting with water to a measurable extent to extract H+ from water and create hydroxide ion. That's how we know if a material is an acid or base today. Same thing. Now what about Ka and Kb for water? Textbooks often follow this up because they say Ka or Kb for water is the same as Kw. That's not right, because they have forgotten the definition of Ka. So let's take a peek, even though it's in the notes. This reaction, of course, corresponds to Kw for water, where Kw for water is simply the molar ion concentration product for hydronium ion, hydroxide ion. 1.0 times 10 to minus 14 if observed at NLC, normal lab conditions. Now take note of this reaction, because it also corresponds to Ka as well as Kb for water. Because establishing this equilibrium requires water to react as a Bronsted acid with solvent water to make hydronium ion and the conjugate base of water. Or from a Kb standpoint, now reactant water as a Bronsted base would react with solvent water as a Bronsted acid to make hydronium ion and hydroxide ion. Same things. So, what's Ka for water? The molarity of this times the molarity of this divided by, not the molarity of solvent water, because solvents and their concentrations are not included in equilibrium constant expressions. But you have to include the molarity of water behaving as a reacting acid. Otherwise, you cannot possibly have a measure of the extent to which water reacted to make hydronium ion. So water, the reacting acid, has to be included in the denominator of this K expression. Water as a reacting base has to be included in the denominator of this expression to get Kb for water. And what's the molarity of water liquid in pure water? You talked about that in discussion class. There's information on this in the notes. 55.3 molar. Does that sound familiar to you? The molarity of water liquid in pure water liquid. Consider a liter of water liquid. A volume of water liquid with which you are quite familiar. What's the mass of this liter of water liquid? What is it? 1,000 grams, right? Density of water is effectively 1 gram per milliliter. So 1,000 milliliters of water, 1 liter of water weighs 1,000 grams. 1 liter. The volume which corresponds to molar concentration. How many moles of water in this 1 liter of water liquid which has a mass of 1,000 grams? You remember the formula mass of water? 18 grams per mole to 2 sig figs, 18.0 grams per mole to 4 sig figs. So I'm going to write 1 mole over the formula mass, 18.0 grams. And I'll multiply that by 1,000 grams. That's the mass of the 1 liter volume. Grams cancel. But it's 1,000 grams per liter. And what happens when I divide 1,000 by 18.02? I get 55.3. The molarity of water liquid in pure water liquid. So the Ka for water, which is the same as Kb for water numerically, is 1.8 times 10 to the minus 16. That's what you get when you divide that by this. And that's the value you see appearing in our handout sheet. Acid-base table. In the notes. Ka hydronium ion. Well, you've learned about the relationship, important relationship, that the numerical value for Kw is equal to the numerical value for Ka for a particular Bronsted acid times Kb for the conjugate base of that acid, which is why, for example, in our acid-base table, where we have a number of Ka values cited, do we need also to cite the Kb values? No. You can calculate any Kb value you want, so long as you got the Ka value included in the table. If I gave you a table of Kb values, you could calculate the Ka values as necessary. So, let's use this relationship to get Ka hydronium ion. Tell me, what reaction corresponds to Ka hydronium ion? What reaction corresponds to Ka for any acid? The acid reacting with water to protonate water and make hydronium ion, while the reacting acid converts to its conjugate base. So it's hydronium ion plus water in equilibrium with hydronium ion plus water. How about that? A no net change transformation, but a transformation which is forever ongoing in water solution. H plus exchange, like hydronium ion protonating water, from a kinetic standpoint, has been observed to occur at about a rate of 1 H plus exchange for a quantity of time that's smaller than a nanosecond. That sound fast? That's damn fast. That's one more reason why we can't do much with kinetics. You know what kind of machinery you need to make measurements on this kind of stuff? It's really delicate stuff. So, Ka hydronium ion 55.3, which is the same as Kb hydroxide ion. And now, a concept which was purposely skipped over in discussion class, because I think it's easier if I tackle it here. A concept which we are going to use regularly throughout the term from now on. It's called material balance. There are different aspects of material balance. The aspect of material balance with which we wish to become familiar in Chapter 18, since Chapter 18 is on Bronsted-Lowry acid-base chemistry, is what are the viable forms of a material, a substance? What does viable mean?
Favored.
What?
Favored.
Favored? Nope.
That can exist.
Can exist. Viable means it's something which can in fact exist and have its quantity observed by measurement. So what are the viable forms of water and solvent water? Dependent upon Bronsted-Lowry acid-base chemistry, which means dependent upon H plus gain or loss. Well, we know if water gains H plus, you get hydronium ion. If water loses H plus, you get hydroxide ion. And those are the species which in fact can exist in water and in fact correspond to hydronium ion, the strongest acid which can be found in water at high concentration, and hydroxide ion, the strongest base which can ever be found in water at high concentration. Because any base is stronger than hydroxide ion, react to convert to hydroxide ion. Any acid stronger than hydronium ion, react to convert to hydronium ion. And conjugate base for the acid, conjugate acid for the base. So, material balance for water and water liquid. Here's the statement I just stated. Is sum of moles of water liquid in a sample of pure water liquid like 1 liter, pardon me, plus moles hydronium ion plus moles hydroxide ion. Have you ever written a Lewis picture for hydronium ion? Do it. Hydronium ion Lewis picture. What's the shape of this thing? I told you. If you need a review of this stuff, it's all in chapter 23 of the notes. You better get at it. I'll ask you questions about structure, shape, hybridization throughout. Trigonal pyramid. Shaped like an ammonia molecule, for example, which is the molecule usually illustrated first to illustrate trigonal pyramidal geometry. But the purpose in the main of my having written the Lewis picture for hydronium ion now is to show you that on the oxygen atom for hydronium ion there's still a non-bonding pair. So another H plus could potentially connect with this non-bonding pair, make a coordinate covalent bond, and in so doing create this thing, H4O2 plus. Is this a viable form of water in water liquid? Well, if it was, we'd have to tell you. But no evidence as yet has been obtained to support the conclusion that this does in fact exist. Got any idea why this doesn't exist? Pardon me. That's a Lewis picture for H4O2 plus. You can write Lewis pictures for species whether or not they exist. Any idea why this doesn't exist? Well, it has to do with charge, I'll grant you that. Does H plus have a substantial positive charge density? Yes. How does the positive charge density of H plus compare to Al3 plus? H plus has a positive charge density which makes the positive charge density of Al3 plus look like nothing. But Al3 plus is 3 plus. H plus is only 1 plus. Why is my statement true? H plus is a nucleus. Ha ha! Boy, is that tiny. You'll learn this in 2045 when you talked about the Rutherford model of the atom, for example. The nucleus of an atom is less than 0.1% of the total volume of the atom itself. And positive charge density on H plus is enormous. So when you glue two ions, H plus ions, which have this enormous positive charge density on the oxygen atom and a water molecule to make this stuff, positive charge concentration, as I see it to be, is far too great. Result, doesn't exist. What about oxide ion? Is that a viable form of water? Oxide ion is certainly a viable form of water in the solid state. There are oxide salts, a number of them. Calcium oxide, for example, is a material which really has a number of important uses. We'll talk about such later on. If you take calcium, pure elemental calcium, and put it in the presence of dry air, so there's no water about, calcium will oxidize in the presence of dry air by reaction with oxygen and make calcium oxide. But if I dissolve calcium oxide in water, do I get a solution containing calcium ions and oxide ions? I get a solution got calcium ions in it. What happens to the oxide ions? You know what the acid-base table tells you? Oxide ions are stronger bases than hydroxide ion. Good deal stronger. So on contact with water, oxide ions react to what extent with water? 100%, and convert to hydroxide ion. So in solution, oxide ion is not a viable form. Now, statement. When we get done with chapter 18, in fact, before we get done with chapter 18, if you have learned what we have offered from this day forward, from that day forward when we get there, you'll be able to take any water solution in any chemistry class you should attend in the future, which invites you to consider the species which can exist in solution, water solution, which can exist in water solution as a function of H plus gain or loss. And there's a bazillion of them. You'll be able to take that solution and analyze it in sufficient detail so as to be able to calculate correctly the molarity of every species in that system whose existence depends on H plus gain or loss. That's a pretty powerful tool. You think biochemists are interested in this? You know that most reactions which take place in the human body, which are necessary to keep us going, depend on pH? You think this might be important? You're damn right. After we program you with material balance, in addition to the Ka, Kb stuff we've already talked about, and we'll talk about in far greater detail as our conversation proceeds, Ka, Kb, material balance, which we're now talking about, and one more consideration which we have yet to get to called charge balance. What do you think charge balance means? Can I go to a bottle, can I go in the laboratory and get me a bottle that just got sodium ions in it? No. Hell no. Because any bulk chemical system, in order to be stable, must be electrically balanced. Must be neutral electrically. Which means in that chemical system, total moles of plus things, or total moles of plus charge, I should say, total moles of plus charge has got to equal total moles of negative charge. It's the only way it can be stable. That's why you can't go to get a bottle of sodium ions all by themselves, or chloride ions all by themselves. It's impossible. So, with Ka, Kb, material balance, and charge balance, when we get to it, you'll then be armed with the information and the understanding that you need to have to do what we just said. Take any water solution and analyze it in sufficient detail to be able to calculate correctly the molarity of every species in that chemical system whose existence depends on pH. That's pretty powerful. So, let's take a look at a consideration which relates to material balance, but which is not discussed correctly on page 1822. So for this conversation, we will relate to what's on page 1822 in the notes, but you need to pay attention to what we now will discuss. And later on I'll tell you why what's on page 1822 is not quite right. Let's consider a solution of a hypothetical acid 8Z, a monoprotic acid. 1.0 liter volume so that moles and molar concentrations are numerically equivalent. In this 1.0 molar 8Z, we shall stipulate that 8Z is ionized 95%. Is that a large extent? Anything bigger than 50% is a large extent. Even 30 or 40% is fairly large. But we'll take large to mean reaction extent exceeds 50%. Small extent means reaction extent doesn't quite get to 50%. Anything less than 50%. So with that having been said, what do you think the K value is for a reaction that proceeds 50% and then equilibrium is established? What's K value? Reaction proceeds 50%. Equilibrium is then established. What do you think the K value is? What I'm asking now is, are you beginning to understand the significance of a K value? A K value bigger than 1 corresponds to a reaction which will go beyond 50%. If you start with a mole of everything in the pot, that'll go past 50% to get you to equilibrium. K value less than 50%, you'll wind up with a higher concentration of reactants than that of products at equilibrium. K value bigger than 50%, higher concentration of products relative to reactants at equilibrium. So what do you think the K value is for a reaction that goes 50%? 1. How about that? Because now the mole concentration ratio, products to reactants, because that's the way we write K's, products up top, K's down below. Hey, the ratio is 1 to 1. K's 1. Okay. This thing goes 95%. Question. If 8Z was a real acid, and we wanted to put it in our acid column of our acid-base table, would we place the formula for 8Z above or below hydronium ion? Because we have defined strong acid as hydronium ion or any acid stronger, period. Above or below? Well, how can we find out? Let's take a look at this equilibrium reaction, because that's the equilibrium reaction established in this 1.0 molar 8Z. Based on 95% ionization, in a solution which has this bottle label, this M sub I value. What, for the 1 liter solution, is the actual mole quantity, same as molar concentration, for hydronium ion? We started with 1.0 moles of this in the liter solution, and this reacted to what extent? 95%. So how much of the 1 mole converted? 95% of it. So what's this going to be? This is solvent, so there's a whole bunch of that. This, 0.05. Let's make it 0.050, since we have 2 significant figures with which to deal. Hey, this tells me that when this thing got to equilibrium, just about all of the 8Z molecules originally placed in the system converted to hydronium ion. Just about all. You agree? Hey, look at the ratio of Z minus to 8Z when this baby came to equilibrium. Well, if you take 0.95 and divide it by 0.05, if my memory is right, you get 19 to 1. Now, back to the question. Is 8Z categorically a stronger weak acid? Rather than pay attention to what's in the notes at this stage of the game, let's deal with this in, I think, a more straightforward fashion by calculating this. There's the chemical form of Ka for acid 8Z. Hydronium ion molarity is 0.95. Z minus molarity is 0.95. So up top we got this. And what do we got down below? We have M sub I minus X, don't we? M sub I is 1.0. X for this case is 0.95. And the equilibrium molarity of 8Z, which is M sub I minus X, which is really M sub I for 8Z less the equilibrium molarity of Z minus, is 0.05. You can do this arithmetic. What value will you get? Anybody got a push button machine? You want to grind this out for us? What'd you get, 18 to 2 sig figs? If that's not right on the nose, I know it's close. We got corroboration for this? 18 is okay? Yep. 18 is okay. That's a pretty big K value. But what's Ka for hydronium ion? So guess what? Even though this thing ionized 95%, it is categorically a weak acid. So we proceed. Now, More on Ka and Kb, again, mainly for the benefit of those who got run off Tuesday by the fire alarm. How do we get Ka values? How do we get Kb values? How do we get any value for an equilibrium constant? How do we evaluate an equilibrium constant? Sometimes I get wise people, students, who say, look it up in the book. Well, someplace along the line, there was no book in which to look it up. Somebody had to determine this someplace. And the only way you can determine stuff is by measurement and experiment, period. There ain't no other way. That's one reason why I like science so much. Forget the lying and the BS. Anybody who makes claims which cannot be supported, even if the claims are exactly correct, is not a scientist. If you cannot verify a claim by experiment and measurement, what you have verified is not scientifically true. Period. I don't care how true it might be, it's not scientifically true. And no scientist will ever accept it as being true. How about that? So, the issue which is considered in the notes and which most of you heard about is, let's imagine we're going way back in the history of chemistry and we'd like to get Ka for acetic acid. Have I yet told you the story about acetic acid arguably being the best known acid of all time? How about that? 4,000 years ago, 5,000 years ago, pre-biblical days, people were at that time interested in making potable spirits. Liquor, wine. I don't know if back then they knew how to make beer, but they knew how to make wine. What's the name for the process that they employed to get the liquor or the wine? Fermentation. But because of the little chemistry which was known at that time, it was impossible to carry out a fermentation process of naturally existing grains like wheat, corn, stuff like that, without at the same time making acetic acid as a byproduct. The fermenters didn't want to make acetic acid, but they didn't know how to escape from it. That's why acetic acid is arguably the best known acid of all time. Because the fermenters made it, didn't want to make it, while they were making the stuff that they wanted to make. The stuff that contained ethanol, the active ingredient in potable spirits. Well, we will go to the laboratory. We shall imagine that we have a method to make pure acetic acid. And with that, we will prepare carefully in the laboratory. Prep, say, because I can make any molarity I want, practically speaking. This solution of acetic acid, 0.300 molar, with water being the solvent. Now, what I'm trying to do to get Ka really is to evaluate K for this equilibrium. You know this. Because by definition, Ka acetic acid is equal to K for this reaction. Because it shows the acid in question reacting with the solvent to make hydronium ion and the conjugate base of the reacting acid. So we will write the equilibrium constant expression in its chemical form, and then we will subject this solution to a pH measurement using a good pH meter. Well, what meters you got in 46 laboratory, pretty good. They'll give you a 2 significant figure reliability if they're appropriately tuned up by the stock folks. And find that for this solution we get pH 2.63. How many significant figures in this pH? How many? 3. How many? 3. How many? 3. 2. pH is a log, isn't it? A log has 2 parts, doesn't it? Characteristic and mantissa. The characteristic are the digital entries to the left of the decimal point, and they serve only the purpose of telling you the power of 10 by which the anti-log of the mantissa is to be multiplied. Woo, is that a mouthful? Did you learn about logs in high school? I believe that part. The comment was not much. Because I find out that students in doing pH arithmetic are oftentimes really confused because they didn't really learn much about logs and how to deal with them. Logs are damned important. They weren't invented to make your life miserable. You know why logs were invented? Do you know the main purpose of logs? What's the main function? The main utilitarian value of logarithms? Don't know that, huh? It allows you to take an exponential equation, and by converting the exponential equation into its logarithmic form, you can now solve it linearly. That means you can solve it by addition or subtraction. How about that? Because linear equations are a hell of a lot easier to solve than exponential equations. That's why logs were invented. That's the real beauty of logs. Okay? So, given that most of you seem not to recognize this pH contains 2 sig figs, the digital entries in the mantissa. If there's a 0 there, that's also significant for a log. This is a decimal point locator. So with this, we take the anti-log to get the hydronium ion concentration. And in so doing, we'll find that the hydronium ion concentration is something times 10 to the minus 3. What is it? 2.3 times 10 to the minus 3. Two sig figs is good enough. Now then, based on this equilibrium, with acetic acid being the only solute in this system, and after having determined the hydronium ion molarity to be 2.3 times 10 to the minus 3, what's the acetate ion molarity? Could you read this thing stoichiometrically? It's 2.3 times 10 to the minus 3. Because this reaction tells you, as this reacts with this, however many moles of this are produced, that's how many moles of this you produced. So with acetic acid being the sole solute, the molarities of these two products have to be identical. So, up top, we got 2.3 times 10 to the minus 3 squared. What do we got in the denominator? Do we have 1.0? I mean 0.300? Do we have this? Is this correct? Is it the equilibrium molarity of acetic acid in this solution? No. What is the equilibrium molarity of acetic acid in this solution? It's this less this, because the concentration of this is a measure of how much acetic acid disappeared and became this. So I'll take this scientific notation form for the acetate ion molarity and convert it into decimal fraction form in order to determine the equilibrium molarity of acetic acid, which is this less this, 0.298. Now I'll do the arithmetic. What do you think I'll get? I'll get 1.8 times 10 to the minus 5. The Ka value for acetic acid you see tabulated in the notes. And I've looked up Ka for acetic acid. The only variant I've ever seen is 1.7. But just about every book I've seen says 1.8. So we'll stick with 1.8 times 10 to the minus 5. Okay? Now then, as most of you have already seen, from this we can make a very important generalization, which is a single solute solution like our acetic acid solution. We can write this. You see how this follows from what we did here? X, the great unknown identifier, corresponds to the equilibrium molarities of each product. Hydronium ion and the conjugate base. For a base, X will correspond to the equilibrium molarities of conjugate acid and hydroxide ion. And m sub I minus X gives us the equilibrium molarity of the ionizing solute. Acid if it's Ka, base if it's Kb. But keep in mind, these relationships only apply if as a solute you only have one material contained which affects pH, like acetic acid in the acetic acid solution, or like ammonia in an ammonia solution. So, let's put this to use. Again, most of you have done this. To calc hydronium ion molarity for 10th molar to 2 sig figs acetic acid. Question. Our 10th molar acetic acid has been prepared from our 3/10 molar acetic acid solution, 0.300 molar acetic acid, by taking 1 part of the 0.300 molar acetic acid and adding enough water until the total volume of the original system has tripled. In other words, you make a 3-fold dilution on 0.300 molar acetic acid to convert it into 10th molar acetic acid. You learned about foldedness of dilutions, didn't you, in 2045 lab? How about that? Think that relates to this? You know the answer. Question. We know the hydronium ion concentration for the 0.300 molar acetic acid. It's 2.3 times 10 to minus 3. So if this acetic acid solution, which is 1/3 as concentrated as this acetic acid solution, can I calculate the hydronium ion concentration correctly for this acetic acid solution by taking the hydronium ion concentration for the more concentrated solution and dividing it by 3? Why not? Why not? Tell me what's going on. You see this reaction? We did this before, now we're going to do it again. Now from a quantitative standpoint. What happens to the extent of ionization of this stuff when you dilute it? When you add more solvent? Do you keep the ionization extent the same? Do you increase it or do you reduce it? What happens to the ionization extent of acetic acid in acetic acid solution when you dilute the acetic acid solution? The ionization extent increases. So you have an effect acting on the system which tends to up hydronium ion molarity and acetate ion molarity. But as we discussed when we're talking about writing equations for reactions in response to question 1810, you can't get something for nothing. You cannot take a water solution of a weak acid, more strong acid, who cares, and dilute it, and in so doing make the hydronium ion concentration increase. That's impossible. Because the dilution factor outweighs the increase in ionization extent factor. But this at least tells us that the hydronium ion concentration for our less concentrated acetic acid solution, this one, is not that number divided by 3. It must be a number which compares how to that number divided by 3. Got to be bigger than that number divided by 3. All right, let's have at it. Because, from a number standpoint, when I look at these expressions, which are each quadratics from an algebra standpoint, if m sub I does not change when equilibrium is established, if m sub I minus x is equal to m sub I, then I can solve this correctly by forgetting the x in the denominator. Does that sound like a fair statement? Well, let's take a look. For this, we'll write 1.8 times 10 to the minus 5 equals x squared over 0.10. In other words, I'm going to believe that the value for x, the hydronium ion concentration as well as the acetate ion concentration, are so small numerically that when you subtract them from 0.10, 0.10 stays 0.10. Let's find out. All I do now is cross multiply and find out that x squared is 1.8 times 10 to the minus 6. So x, which is my hydronium ion molarity, as well as my acetate ion molarity, is the square root of x squared, which is x, as well as the square root of 1.8 times 10 to the minus 6. Now what about the square root of 1.8 times 10 to the minus 6? What's the square root of 10 to the minus 6? I'm listening. I don't want to see any push-button calculators. 10 to the minus 3. What's the square root of 1.8? No calculators, except this one. Roughly. Square root of 1.8. I'm listening. What's the square root of 2? 1.4? Good enough, the 2 sig figs? And the square root of 1? Ooh, that's a tough one. 1. And 1.8 is smaller than 2, isn't it? So we know the square root of 1.8 is a number that's about, but not quite as large as 1.4. That's the square root of 2. Okay? Now then, did you learn the squares of numbers from 1 to 25 in school? Because if you didn't, you should have. What's 12 squared? What's 13 squared? What's 14 squared? Yop! You know what yop means? You ever see Dead Poet Society? Wonderful show. I want you to yop. Speak loudly and boldly and brashly to indicate that you know what you're talking about. 13 squared, 169. 14 squared, 196. Therefore, which is closer? 1.69 or 1.96 to 1.8? Which is closer? 1.69 or 1.96? 1.69. So the square root is 1.3 times 10 to the minus 3. And this leaves us with one final question for this problem. Is this the correct hydronium ion concentration for this solution? Well, here's 0.10. And this is what we got by neglecting x in the denominator. If I take 0.0013 from 0.10, what is the answer? What is the answer? 0.10 is the answer. So guess what? What we did is correct. We'll pick it up from this point next time.